Hey everybody, this is your 4.4 pre-calculus video. So what we're doing on this one is properties of rational functions. And so we have 1 over x, because x has to be in your denominator. If you were to graph it, it'd be on the left and right like that. And you'd have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Also, like we've discussed before, this is an odd function because it's symmetric to the origin. Symmetric to the origin. And your domain would be basically everything but 0. So you have negative infinity, 0, union, 0, infinity. And for your range, it would be from the low to the high, anything negative, so negative infinity, 0, but not including 0 because you have a horizontal asymptote there, and then 0, infinity. So all of those have to have parentheses, not brackets. Now for 1 over x squared, both would be up. It would be an even function because it's symmetric vertically across the y-axis. Your domain would be the same as the regular one, where it's negative infinity, 0, union, 0, infinity. But this time your range would only be 0 to infinity, because it can't be negative. So those are some similarities and differences. Now, if you were to have negative 1 over x, that'd be odd, and it would look like that. And if you had negative 1 over x squared, it would be down like that, and that'd be even. Okay, so that kind of covers our domain and vertical asymptotes, as well as horizontal. Now, sometimes you're going to have to do the ratio or fraction of the numbers. Like if you had something with 6x something, or 6x squared, and you had 2x squared minus 4, you ignore these numbers to the side and you just do your ratio. So 6 over 2 would be 3, and that'd be your horizontal asymptote. There's also an oblique asymptote, or we call it slanted, and that'd be if your degree is 1 higher, like if you have x cubed over x squared. So your slant would be y equal x. Okay, so again, why we're studying this is that integers are positive or negative whole numbers. Like you have to think of them as not just a fraction or a decimal. The only time it'd be a fraction is if you did like 8 over 2, which really is 4. Then 4 is an integer. But normally fractions are not integers. Ratios of integers are called rational numbers, which include all integers plus fractions like 3/5, decimals like 0.6, and repeating decimals like 0.3 repeat, which is 1/3. On the other hand, it does not include square roots like the square root of 5, since that has a decimal that goes to the end of the calculator screen without repeating, and also it does not include pi. Those are called irrational numbers, or not rational. And remember, we recently studied polynomial functions, and ratios of them are called rational functions. And one other thing is the other name for rational is called reciprocal, because instead of x, it's 1 over x. And instead of x squared, it's 1 over x squared. So basically, x is in your denominator. Now, for your definition, the most important part is having to do with your domain. And you have to have your denominator set equal to 0 and solve. So then the technical definition of vertical asymptote is that as x approaches some number, then the y value, in this case r of x, approaches infinity. Either infinity going up like that on both sides, or one side up and one side down. So for example, when we say both are up, how we could write this, if you think of this as -5 right there, you could say as x approaches -5 from the left. So you have a little minus sign which indicates it's to the left, and so you're talking about things like -5.001. Okay, so that's x approaches -5 from the left. Then y approaches infinity because it's up. And as x approaches -5 from the right, because that's plus, you would think of that as -4.999. In this case, also y approaches infinity because it's up. So these are going to help you when you get to study limits in calculus. Now you also have like x approaching 0 from the left, which would be like -0.001, and you can have 0 be approached from the right, which would be +0.001. So be careful, like if you're actually moving left or right, your numbers are going to be different, like trapping the vertical asymptote. But when it's 0, you're just going to have negative and positive of the same thing. And technically, you can have as many zeros before that as you want, like 0.00001. Okay, so with all that prep, there's a little bit more on locating the vertical asymptotes, and basically it's going to be a real 0, and x minus r is going to be the factor. So what we're saying is, like, if you have 1 over x plus 3, we're going to set the denominator equal to 0, so x plus 3 equals 0, and get x as -3. And in this case, that'd be a vertical asymptote at x equal -3. And so that means x plus 3 is a factor. So now there's other times when there'd be a hole in the graph instead of a vertical asymptote. They're harder to see on the calculator. You really need to analyze the graph and know what you're looking for. So one example of that type problem is if you have x plus 2 times something in your numerator and x plus 2 times something in your denominator. Notice these two completely match, and so there would be a hole right there. But then you'd have a vertical asymptote at x equal 3. Now, in that case, it's going to look like this. Do a parentheses, x plus 2, another parentheses, x minus 1, divided by, now on my denominator, I'm going to do a double just to make sure it's all safe. That's what I have here. And so I have x plus 2, and then I have an x minus 3. So what happens in that case is it's going right 3, and you have a vertical asymptote. And if you look in your table, at 3 it's undefined. Now look, at -2 it's also undefined, but it looks connected. And even if you try zooming in, you will not see a hole in the graph. So even if I go to trace, I'm walking my cursor over to -2, and it skipped over it. That's why sometimes I don't like using trace, because you can't tell. Now it is useful for telling you, like, oh, there's my y-intercept, and there's my x-intercept, which is the 0 of the graph. But it doesn't really tell you everything. Now that's an example where you see clearly that the same thing is on top and bottom. So your graph would actually, if you graph it on paper, we'd put a little hole there so it's not a continuous part. Now sometimes it's going to look harder, like x squared minus 9 there and x plus 3 on bottom. So then you'd have to factor that numerator, and then the x plus 3 would cancel, and so it'd be a hole instead of a vertical asymptote. So when we do that, that's going to look like x squared minus 9 divided by parentheses x plus 3. Now normally, since it's x squared, it'd be like going up quickly, but this just looks like a straight line. In fact, the y-intercept is -3, and it's just linear. It is a slope of 1, but the y-intercept is -3. So when you have 1 degree higher, you're going to look like that. And you can confirm it in the table if you want. Go in your table, add -3, it's undefined, even though it looks continuous. So the actual graph itself could be misleading. You have to use your table and use your knowledge. So even though you see your y-intercept's -3 and your x-intercept is 3, it's not continuous. It looks linear, which is continuous, except it's not, because you have a little circle there where it's undefined. So be careful on that. So now let's think about the basic or parent rational function, 1 over x. If you set your denominator equal to 0, like we've said before, you will see what values to not include in the domain. The domain would be all reals except for 0. So again, look at the graph. It would look like that. The vertical asymptote is related to where the denominator is undefined, except when it's a hole in the graph. Now, on ones like this, you'd have x plus 2 over 2x minus 3. So let's graph that. X plus 2 over 2x minus 3. Notice your degree of the denominator is not bigger and your degree of the numerator is not bigger. So when you have this circumstance, your asymptote is not at 0. In fact, if you just do 1 over 2, that's going to be your asymptote here. The reason is because think of your x's as canceling, and so it's a half. Now what you can do is you can look in your table and you can see these values on the left side are getting closer and closer to 0.5, and the same thing on this side. Getting closer and closer to 0.5. Now by the way, remember, if you don't want to hold down that button too long, you can go to table setup, so table, then 5, and just start your table at 1,000. And I'm still close to 0.5. And I'm above because I'm on that side. But now, on the other hand, if I go to my table settings and I go to -1,000, then I'm below, and so I'm at 0.498. Okay, so that's how that works. And I mentioned the same thing here about approaching 3 from the left would be 2.999, which is 3 minus, and 3.001, which is 3 plus. So it's called proper if your degree in the denominator is bigger than the numerator. Another way to say the same thing is your degree in the numerator is smaller than the denominator. So when you have that, you will have y equals 0, which is the x-axis, as the horizontal asymptote. Now, That's again restated right here. It's kind of like a duplicate. And I know it looks really technical right there, but if it's greater than or equal to, then it's called improper, and you'd have to use long division. You can't just use synthetic division because you'd have to watch out for your zero placeholder and watch out for your extra terms. So this is x cubed minus 2x plus 1, so you have no 0x squared term. And this is x squared minus 4, so you have no linear or x term. So when we do this, we'd say x cubed divided by x squared gives us x, and then you'd multiply it out. X times x squared is x cubed, x times 0x is 0, and x times negative 4x is negative 4x. And remember, since we're using long division, that it'd be implied subtraction with those canceling. And this would be negative 2 minus a negative 4 or plus 4, which gives you 2x, and then you bring down the 1. So the 2x plus 1 would be your remainder. So you have your answer or quotient x plus 2x plus 1, all of that divided by this part, x cubed minus 2x plus 1. Now, if they are equal, then you just do your ratio like I said earlier. Like if you have 4x plus 3 over, let's just say 2x minus 1, then it'd be 4 over 2, which is 2 for your horizontal asymptote, be y equal 2. So again, graphing that to show you parentheses 4x plus 3 divided by parentheses 2x minus 1. That one has your horizontal asymptote at 2. You can just put 2 there, and there it is. Now, if it's 1 bigger, it's slanted or oblique. You can have a parabolic one also if it's 2 higher. So, for example, on that, you could have something complicated like x to the 4th minus 3x. I'll just keep it like that. Divided by parentheses x squared minus 6. So that one looks kind of funny, but that's what happens when it's 2 higher. If you had some more shifting, it'd look even weirder. So that'd look even weirder like that. So the more terms, the harder it looks. All right, so now let's go over a few of the definitions. Need this to come into focus. Okay, so if it's a rational function, if the degree of the numerator is smaller, then it's called proper. So again, we think of just 1 over x. You could think x over x squared over x cubed, etc. with any pluses or minuses, because that part doesn't really count. On the next part, the graph of a rational function may intersect a horizontal asymptote. You might think that's false because of what we've seen. Like earlier when we graphed some, like this, for example, it's not crossing the y-axis, the x-axis. But you could have a type graph that I've seen that goes down and then it has an asymptote on just one side. So that is going to be a true statement. I know that y'all wouldn't know that without me telling you. That's why I'm telling you. So it is possible to intersect the horizontal. It's not possible to intersect the vertical. So if you have a vertical one here, it's either going to go up like that, or one side would be down and the other side would be up like that, or like even this side's up and this side's down. So those would be like never intersecting your vertical asymptote, because you can say it's undefined in the table. So it never can intersect. Now, if it is proper, which we were talking about earlier, then its asymptote is y equals 0, which is considered the x-axis. Don't get confused with the x equals 0, because that's the y-axis. So again, they're opposites. Okay, now moving on. If the degree of the numerator is the rational function is the same as the degree of the denominator, then the ratio gives rise, or it tells you the horizontal asymptote. That is true. That's something we mentioned, because if you have like x plus 7 over 2x minus 2, that would have your ratio 1 over 2. So it would look like that. With x squared also, like if you have 2x squared in something and 3x squared in something, it'd be y equal 2/3. So like this, if we had parentheses 2x squared minus 3x plus 5, divide by parentheses 3x squared plus 4x minus 1, you have this horizontal asymptote, and if you look in the table, it would get closer and closer to 2/3. I guess I ought to just do my table part. 2, then 5, and then make this like negative 1,000. And you can see it's 0.668. And if you go even more, because I just made up this random one, but if you go even more with more zeros, you see that, then I'm at 0 and a bunch of 6s. So that's your 2/3. And it'd be the same thing on the other end. If I just change this setting, menu table setting, to be starting at positive a million, or even bigger, billion, whatever, then you can see that. So it is at 2/3. It's not at 0. Okay, so now getting to the little bit, the ones that are not just definitions. What you do to get the domain is you set your denominator equal to 0. This is called the zero product theorem. And so basically you say x minus 9 is equal to 0, because let's say this one's 0, so then x would be 9. And on this side you set x plus 9 equal to 0, so it's negative 9. You don't even have to really do that work, just see that they're opposite signs. And the domain would be that it's not those. Not where there are vertical asymptotes or holes. In this case, there are no holes because there's not x minus 9 or plus 9 up there. Now on this end, you want to set your denominator equal to 0, and so we have x cubed minus 125 equals 0. So move it over, you get positive 125, then take the cube root and you get 5. So if we go to calculate, and then this button right there, control caret, you could say the third root of 125, and there's your answer, 5. So basically it's not 5. In other words, you could say 5 times 5 times 5 is 125. So your graph would be everything except for 5. So let's show that. X divided by parentheses x to the third power minus 125. Now make sure you put your parentheses around that when you're putting your fraction, so then you can see there's a problem at 5. It says an undefined. So it's real quick if you know what you're looking for. Or you could do it this way. Now this next one, it wants you to find the domain. So we set our denominator equal to 0, so 6 times x squared minus 64 equals 0. You would divide by 6 to just get 0, and then take your square root, so plus and minus 8. So your domain is everything except for positive and negative 8. So now, like, you might actually have to put that in a weird notation later on, which would be like from negative infinity up to negative 8, parentheses, union from negative 8 to 8, union from 8 to infinity. So that'd be the more complicated form, and you might have this year or you might have it next year. Also over here I say zoom out if you're using the graph to see both sides, because what if you had 12 and negative 12? So that's what I was getting at, because I don't know what your numbers are going to change to. So let's graph it and say 5 parentheses x squared minus 7x minus 8 divide by, I'm going to do a double parentheses, and I need to put the 6 there in between them, and I need the x squared minus 64 right there. So then I can see a negative 8 issue which says undefined, and a positive 8 issue which says undefined, but that looks like it must be a hole in the graph. Now, what you might need to do is factor. Sometimes, like, if you want a set pattern, they may say factor it first. So that would be factored in the numerator to x plus 1, x minus 8. And the denominator would factor into x plus 8, x minus 8. So then you can see that you would have a hole at 8. So it's not actually a vertical asymptote, it's just a hole. But this end is. And I was saying you could zoom out. There's that asymptote, and there's no asymptote over here. Okay, so that's a lot of information on that one. Let's continue. And on this one, they're showing you a graph. They're not really giving you the equation, but you have to interpret the graph. Now, what I was going to say about this is that the little box doesn't really count, because I looked at this on Math Excel on the computer, and that part's not visible. All you really have is this part and that part. It tried to make it something it wasn't. So this one would be a hard one to do on paper, unless I mark out that box like that. Okay, so what you can see though is your domain is everything except x equal negative 1, and your range would be everything except for positive 1. So that's how these come into play. And now it wants the x-intercept, which would be from the 0, 0, which means your x-intercept is 0, and it also means your y-intercept is 0. Now your next part is, they say find the horizontal asymptote, and I said over here as a note, it's related to the range. So the range part said y not 1, and so the horizontal asymptote is y equal 1. In the same way, the vertical asymptote says x equal -1, and I say related to domain. So this is x not -1. So again, those are related, and there are no slant asymptotes or oblique on that problem, because if you have a horizontal, you're not going to have an oblique. So that's why you would choose that there's no no oblique asymptote for that one. Now this is one where, again, you have extra lines on your paper. It's a little confusing. That's why sometimes I prefer the online assignments. The graph really looks like this, where you would have your -3 and 3 as your dots, but it's going like that and like that. So your domain would be everything except for 0. Your range is everything because it is continuous. Your x-intercepts would be the -3 and 3. You would not have a y-intercept though. The reason is because the domain is x not 0. So you might want to make that note. If your domain is x not 0, then you're not going to have a y-intercept. Okay. And also in this problem, you don't have a horizontal asymptote, but you would have a slanted asymptote. Your vertical one would be x equals 0, like we said before. Your oblique one, in order to find out, you'd have to use the graph where it says 0 here, and it says 2, 10 there. And I know your numbers are going to change, but remember, think about rise over run. So this would rise 10 and run 2. So based on that, if you do 10 over 2, you get 5. And our y-intercept would have been 0. So we have 5x. So that's your oblique. On this one, they want you to say which one is it. So here we have, see, sometimes I don't like paper assignments. In this case, you can see you have an A, a B, and a C part of it, and there's no D. So let's graph this by hand. X minus 1 squared means it's going to be right 1, and that's where your asymptote's going to be. And based on being squared and positive, it's completely up, and it's proper, which means it's this way and this way. So what I said was proper, so it's like a horizontal asymptote at y equals 0. Both sides are up since it's positive 3. And you'd have to choose the correct graph. Here it is. 3 divided by parentheses x minus 1 squared. So there's what I was saying. So pick the correct graph. On this one, let's graph this. -1 divided by parentheses x squared plus 8x plus 16. So here both are down because it's negative, and your asymptote is probably at -4. Let's look in the table. Sure enough, -4. So how I could have thought about that is this would be -1 over x plus 4 times x plus 4, or think of that as -1 over x plus 4 squared. So that would mean both are down. So for the Texas Tech reference, guns down, it's just like that. And the asymptote, vertical asymptote at x equal -4. Because if you set your denominator equal to 0, that's what you get. Okay, and then 13. This one we have 6x over x plus 19. For your horizontal asymptote, you do 6 over 1, or think 6x over x, so that's 6. And for your vertical asymptote, you say x plus 19 equals 0, so x is -19. So the -19 goes there, and your 6 goes there. And there's no oblique. Okay, and then on this one would be a little pain to factor, but I think I remember what this is. I know the denominator would factor pretty easily to x minus 4, x plus 1. This one's the difference of two cubes, and I think that would go to x squared plus, dang. Okay, well, let me do long division. You probably don't have to write this, but x cubed plus 0x squared plus 0x minus 64. So to do long division, these cancel because it's implied subtraction. This is a positive 4x squared. You bring down your 0x. Then you need 4x next. So that's 4x squared minus 16x. Again, implied subtraction, so it cancels. And this is positive 16x minus 64. So we need a 16 there. So 16x and negative 64. So that does work. So that's what that would factor into. And then these are holes. You have a hole at x equal 4, not a vertical asymptote. And you can confirm that just by graphing it. So on our graph, we have x to the third power minus 64, divide by parentheses x squared minus 3x minus 4. I need to change my window. I'm actually not going to change my horizontal part. I'm just going to do zoom fit. So 4 and then A. There's my zoom fit, and there's my graph. So we have a vertical asymptote at -1, because if this factored to x plus 1, then that's the -1. Again, if you wanted to, look in your table. -1 shows undefined. And then it's no horizontal asymptote because, or since, it's x cubed over x squared. You would have an oblique one. So in order to get the oblique, you'd have to do long division. Now this part you might want to write, probably do want to, x cubed plus 0x squared plus 0x minus 64 divided by x squared minus 3x minus 4. So what I'm doing is this long division for the oblique asymptote. So x cubed divided by x squared is x. So again, that's x cubed. Then x times negative 3x is negative 3x squared. And x times negative 4 is negative 4x. Now you're implying subtraction. So this cancels. This turns into positive 3x squared. And this turns into positive 4x. Now you just bring down the 64 that's negative. Now what you need is to put a plus 3. And so 3 times x squared is 3x squared. That's your goal, to match the first term. Everything else could end up being a remainder. Then 3 times negative 3x is negative 9x. And 3 times negative 4 is negative 12. So again, this cancels. This would end up being 4 plus 9, which is 13x, and negative 64 plus 12, which is negative 52. And there's no extra terms. That's it. So you just use this part for your answer. So that's the x plus 3. So, in other words, it's okay to not have a denominator of 0. It's okay to not have a denominator of 0. So, in this case, I didn't mean denominator. I meant a remainder. I think I did that once before also. It's okay not to have a remainder of 0. It's the opposite of synthetic division if something is a 0 of the graph. Okay, so that's your quotient, which is your answer. Here's another one. And on this one, we have x squared over x to the 4th. So is it proper? Yes, since the denominator degree is greater. And because of that, you put your horizontal asymptotes y equals 0. So you just know it without even graphing it. Now for this part, for your vertical asymptote, you can say x to the 4th minus 1 equals 0, because you're setting your denominator equal to 0 for finding your vertical asymptote. And so then we say x to the 4th is 1. So then x would be the 4th root of 1, which is plus and minus 1. Now, I know y'all would probably just put 1, and in your calculator, if you do it this way, you do n to the x and put a 4 there, put a 1 there, it's only going to show you positive 1. But that's misleading because it only shows you what they call the principal root. So what you'd need to do is to graph it to double check, and you go x squared divide by parentheses x to the 4th power minus 1. And so that's where you can actually see it's something at negative 1 and 1 with the vertical asymptote. So that kind of looks like that graph. Sort of looks like a rational function with a parabola. So your vertical asymptotes are at plus and minus 1. You have a horizontal at 0, and there's no oblique because there's nothing slanted. Now on this one, let's set our denominator equal to 0. So 2x is negative 3 and x is negative 3 halves. If I were to graph this, we're either going to have a hole at negative 3 halves or we're going to have a vertical asymptote there. So let's find out. If we do parentheses 8x squared plus 6x minus 9, divide by parentheses 2x plus 3, oh, it looks like a straight line. So if the graph looks like a straight line, then it's a hole on this problem because your degree is 1 greater. So now, mathematically, how would we know that? Well, let's try factoring this 8x squared plus 6x minus 9. So you remember when we're factoring, one option would be, say, 8x and x. Another option would be, say, 2x with 4x. And that's what we're going to end up having here. Now we need 9 for our back part, and so we need a 3 and a 3. And since it's a negative 9, one of them has to be positive and the other negative. So then we would guess and check. Is it going to be 2x minus 3, 4x plus 3, or is it going to be 2x plus 3, 4x minus 3? So let's see. 2x times 3 is 6x. What I'm focusing on is my O term, which would be 6x, and my I term would be negative 12x. So that gives me negative 6x, which is not what we want. We wanted a positive 6x. So now let's try it this way. Again, focusing, well, let me do the whole FOIL part. For the f, it's 2x times 4x, which is 8x squared. And for the O part, it's 2x times negative 3, which is negative 6x. For the I part, it's 3 times 4x, which is 12x. So I put a plus 12x. And for the last part, it's 3 times negative 3, which is negative 9. The part I didn't put was 2x times 4x, but that's kind of like self-explanatory. And so in this case, for the O and the I, you have negative 6x plus 12x, which does give you 6x, which is what we wanted, because everything else works. So how do we interpret that? Well, if one side was 2x plus 3, which matched, then this part is your other answer. It's right here, 4x minus 3. Now, no, that one's a little more complicated, but you might want to use your graph. Remember, it's algebra, so there's other ways to do it. I mean, I know I'm supposed to teach you this way, but remember, you can go in your calculator and go to your y-intercept, and it's negative 3. And then you notice in your y column, it looks like you're going up 4 for every time you're going right 1. So then you can think, hey, I wonder if that's 4x minus 3. And so then you can go to your tab, say 4x minus 3. It turned red and now purple because it matched. And your y columns match between the red F2 and the blue F1. So even 4, 13, there's another 13. Okay, I know that's a lot of information, Take your time and go through it. Hope that helped.